Thank you. So today we're talking about optimisation. Last one, you have done optimisation a bit last year, and you'll notice the degree of complexity is going to increase a fair bit. Some of these questions are quite challenging. The hardest part is formulating any equations you might need, but once you have the equation, then the processes are all the same. Okay? It's just finding the derivative, finding the roots, drawing a sign diagram, and stating the optimal solution. Alright, so I've got process written down there, I think, in our notes. Yeah, construct the relevant equation. Okay, that's the hardest part, always the hardest part. And I've got some formulas that you may need there in some of the questions in the textbook. Okay, so we've got a manufacturer makes X TVs per day. The profit is given by this equation. Use calculus methods to find the number of TVs that provide the maximum profit. So if you're going to graph this equation right, it's going to look something like this. Okay, how do I know that? Okay, just by looking at it. Let's get you to think about this. It's a quadratic, which means it's a parabola. It's got that parabolic shape. It's either opening upwards or downwards. It's got a negative a value, which means it's opening downwards, and it has a y-intercept of minus 720. Or is it plus 720? I reckon that's supposed to be plus 720. We'll see how we go with the minus. We'll trust it. So excuse me, that should be down here. All right, there we go. So it's going to look like that, okay, where this value is minus 720. And the question says, what value of x is the number of TVs, and on the y-axis, we've got profit. Okay, so what it's saying is the profit that we're going to make with regards to the number of TVs we make. Okay, and let's think of some reasons here. Okay, if we don't make enough TVs, then we're not even going to break even. Okay, if we're making $0 profit, then that means we're breaking even. That the amount of money we're making is paying for the costs of the materials and the running of the shop and that. So, I mean, you can't even anticipate. Why would it doesn't it just make sense that the more TVs you make, the more money you make? Well, perhaps if you make more than this many TVs, you have to pay your staff overtime. You're going to have to, you need time to repair the equipment. And if you're making this many TVs, you're not repairing the equipment, which means the equipment's deteriorating more quickly, which means, so there are reasons for it. But we need to find why is this value the maximum cost. So the way we're going to do that is using calculus methods. Okay, that means we're going to find the derivative, draw a sign diagram, and note any optimal solutions. So P dash of x is going to be minus 0.044x plus 11. Okay, we're going to draw the sign diagram of that. Now this is the equation of a line. And we don't need to consider negative values of x, all right, because we're making TVs. The lowest amount of TVs you can possibly make is 0. So often, not always, but more often than not, in optimisation, the optimal solution has to be greater than 0. All right, obviously we can't make negative TVs. And it's the equation of a line, and its root is 25. So I was like, well, what value of x makes that equal to 0? 25, we can solve that, we can graph it. And the other thing is, this is a line that has a negative slope, which means if you were to draw its graph, it's going like that. It's going downwards, and so we've got going from positive to negative. Now, excuse me, it's 250, not 25. I forgot that 0. And so what that means is on the graph, okay, this is the sign diagram of the derivative. This is P dash of x. It's going to increase until we get to 250 and then start to decrease. So we have maximum profit when we make 250 TVs. Okay, so we can make that statement. Max profit at 250 TVs. What is that profit? What is the maximum profit? Well, this is our profit equation. So we're going to plug this 250 into our profit equation. We're going to find P of 250. When we make 250 TVs, how much profit are we making? So I'm just going to put 250 in here.
Where did you get the 250 from?
Here, I found what is the root of that equation. So I solved this.
Okay.
Yeah. So I'm making a bit of a jump to there. So there's a number of ways you can do it. You can do it manually. You can just graph that line, g solve the root, away you go, you've got the sine diagram. Because what we want is the sine diagram of this equation. Okay, so we've been doing that heaps, that's why I sort of brushed over it reasonably quickly. But I'm happy to go through it a bit if you want. 250 squared plus 11 times 250 take 720. 655, and I think it's in thousands of dollars or something, is it? We're not given a unit, so we'll say $655,000. So we have to look at the unit that we're given. Okay, question 2. Farmer wants to build a duck enclosure against the old shed. So here's the shed, here's going to be the duck enclosure. We're familiar with these problems, we're doing them a bit in year 11. Find the dimensions that provide the maximum area for the ducks. So we've got 200 metres of fencing. Now with a question like this, you might be asked to show that the area is given by this. Okay? And so like obviously the area here, the area of this enclosure is going to be x times 200 take 2x, which is 200x take 2x squared. But like, how do you come up with these measurements here? Like if you're given x there, what's this side going to be? Well, we've got 200 metres in total. This is x and this is x, and so when we add up all the lengths of the perimeter, it's going to be 200. So that length has to be 200 take x. We've got our area here. All right, so process, develop the equation, find the derivative, find a dash. Okay, draw its sine diagram. All right, again, it's the equation of a line with negative slope. Now, what does it say? All right, so remember with these, we've got to make sure we answer the question. So I think all that maths is okay, but the question says, find the dimensions of the duck enclosure. So the dimensions mean what is the length and then what is the width. So if we've got 50, then this length here is going to be 200. Take away 2 times 50 is going to be 100. So therefore the dimensions are 50 by 100. All right, so let's have a look at then the Coke one. All right, so this is one we did last year, isn't it? I might actually, let's leave that blank, okay? Let's leave that blank. You guys can come and have a go at that in a moment. What I think I would like to do is go through a few of them and just talk about how we're going to develop the equation around it, okay? Give you some hints and clues. So, can we all open up 3G? And you're welcome to copy down, you're welcome just to watch, but I might just talk about a few questions and how we develop the equation because that's the trickiest part, okay? Now I promise you in the test with these optimisation problems, we're always going to give you the formula. So even if you can't figure out what this relationship is, you can still perform this whole process, okay? This is, like let's say this is a 6-mark question, there's 4 marks there. Okay, so you're not getting those 2. And so this is perhaps a skill we need to practice because this process isn't particularly complex and you've sort of done a fair bit of it in 3C. It's just extending it a little bit further. So let's talk about, I'm not going to talk about question 1, I think that's going to be a little bit easy. I'm going to talk about question 2, which says we have a circle and we've got a rectangle drawn in it. And part A says, find the area of ABCD in terms of x only. All right. So A, B, C, D, O. This is the centre of the circle, and this is x, and that's a right angle. Okay. Now the other piece of information we're told is that the diameter is 10, so the whole way across the circle is 10 centimetres, which means the radius is 5. Alright, so here's what we are going to do. We're going to do some trigonometry. Alright, we are going to find, let's put, I don't think they've got a point there, let's put a point there called P, and that's going to help us communicate, oh, they've got N. That's going to help us communicate our answer, okay? So we're trying to find an expression for the area of this rectangle, alright? Now hopefully what we're sort of seeing here is with Pythag, we can find this side, Cn, alright? We can come up with an expression in terms of x for Cn, and then this length here is just going to be 2 times Cn, alright? I think we're told it's halfway. $90 degrees, so I mean that's a deductive geometry theorem, so it has to be. And then we can do the same for finding DC. Alright? Well, BC is even easy. Like if that length is x, then that length is x. So this whole length has to be 2x. Right? And the area of this rectangle is going to be BC times CD. Alright? That is the length there times that length there. So we've already got 2x. We need to come up for an expression for CD using Pythag. So I'm just going to call that Cn. That's fine, we can call it Cn. And if we've got this right in front, let's extract it and let's just make it as simple as we can. This is Cn, this is x, and this is 5. Now we're trying to solve for Cn. The simple statement with Pythag is x squared plus Cn squared equals 5 squared. So to get Cn by itself, so Cn is the square root of 5 take x squared. So therefore CD, that whole length there, is 2 times Cn. Which is 2 times the square root of 5 squared take x squared. If I'm going too fast, stop me.
Couldn't we cancel the squares and the roots? Yeah.
No. You can only do that if it's a single term. Alright, because there's multiple terms, we can't. Okay, so is everyone okay with that? We found Cn, CD is 2 times Cn, so we've got CD, and then we're going to plug that up here. So we've got 2x times by 2 times the square root, I'll change it to 25, 5 squared is 25, and so that's going to be 4x square root of 25 take x squared. Alright, so here they haven't given you the equations. I promise you we'll give the equation, even in the exam. They don't often have optimisation problems in the exam. But if they do, I will give you the equation. Alright, and so then for B, alright, this is the area. For part B, you're going to differentiate, draw the sine diagram, find the optimal solution, and then state the answer the question. Alright, so I'm just going to go through a few of part A. Any objections? I'll just stick it around. This here's a bit of a hazard. Let's shut that out. Okay, yes, Raj.
How did you get 2x for BC?
Oh yeah, so if that length is x,
Yeah.
then that length is x, and so the whole length has to be 2x.
Yeah.
Okay, let's have a look at 3, and we'll probably talk about parts A and B. Alright. We've got a 2-litre box, has a square base and an open top. Its dimensions are labelled. Alright, so it's got a base, which is x, and a height, which is y. Alright. Explain why y equals 2000 on x squared. So firstly, the volume of this box is going to be x times y, which is x squared y, centimetres cubed. right? And centimetres cubed is equal to 2 litres, and 2 litres, which is 2,000 centimetres cubed. So x squared y is 2,000 centimetres cubed. And so x squared y is 2,000, and therefore y is 2,000 on x squared. Okay. Show that the surface area of the box, okay? So the surface area of the box, does it have a lid, open top? Okay, so you've got to read those things. Does it have a lid or not? It says open top, so it doesn't have a lid. It's got a base and it's got 4 walls. So when we're thinking about surface area, we've got to go, well, the base, the bottom of it, is just x squared. And then there's 4 walls, and all the walls are the same. All the walls are x times y. So there's 4 walls, which are x times y. We've come up with an expression for y. That's this one here. So then the walls are going to be 4 times x times 2,000 on x squared. We'll simplify that. That's going to be 8,000 on x. All right, x at the top, x at the bottom, so one of them is going to cancel. And then 4 times 2,000 is 8,000. And so then the total surface area is just going to be the base plus the walls. TSA for total surface area. So what have we got? X squared plus 8,000 on x. Right, and so it says, show that the equation is this, and this is how we're doing it. You know, we're making these sorts of arguments. Here's the base, here's the walls, total surface area is the walls, the base plus the walls. Right. I will not talk about 4. I think we can do 4 because we're just given an equation, we don't have to develop it. I will talk about 5. And we'll see how we're going. Okay, any questions about that one? All right, so you've got your surface area equation, and then you're just repeating that process. Differentiate, draw the sign diagram, state the optimal solution. Okay, so here we have the curve e to the minus x squared. All right, and it says infinitely many rectangles can be drawn there. Determine the coordinates of C such that the rectangle is the biggest it could possibly be. So there's the y-axis, here's the x-axis, and it's saying here we've got A, B, C, D. What are the coordinates here such that the area is maximised? All right, so the area of this rectangle then is going to be AD times CD. All right, so that length times that length. And so what I want you, the way we're going to come up with this is let's think about what is the coordinates of C first. All right, firstly, it's going to have some x value, x, and it's going to have the corresponding y value. What is the y value? If we have x, then the y value is just going to be e to the minus x squared. If we have the y value 2, if we have the x value 2, the y value would be e to the minus 2 squared. If we have the x value 3, e to the minus 2 squared. So if we just say x, it's going to be some number. We don't know what it is. All right. Now, what that means is that the distance from here to here is x. Okay, that's the distance from there to there. And the distance from here to here, the y distance, how vertical it is e to the minus x squared. All right. Now, it's symmetrical about the point of origin, which means the distance from there to there is the same as the distance from there to there. We're talking about magnitude. Okay, we're not talking about direction. We're talking about how big is that. That's x, that's x. And so then the area of this rectangle, or AD, we can see is 2x, and CD is e to the minus x squared. Okay, so you've got the equation for the area of this rectangle. saying for any, wherever that point is, for any x value, this is going to give you the area of that rectangle there. You could do the rectangle here. Okay, you could do the rectangle here. But it's saying, what are the coordinates that are going to maximise the area of the rectangle, make it the biggest rectangle possible? All right, I might jump ahead to, so let me just forewarn you, both question 6 and I think question 9 as well, I think they use trig identities that belong to the specialist maths course, okay? So they're not trig identities that you need to know, all right? That being said, okay, maybe I won't make that discussion. We can talk about that later. We're a bit pressed for time, so we'll talk about that a bit later. Let's jump ahead to question 10. Okay, question 10 is a good one. They've had, like you'll see a couple of these in the practice tests. So, and then you'll be able to have go at 11, it's reasonably similar. So question 10 says there's a pump house located at some point X along the river. X, N, and M, 2 kilometres. 1 kilometre, 5 kilometres, all right, so what we've got is we've got 2 pipelines. So this is the river, isn't it? This is the river here. That's why it's coloured in blue. And what we want to do is we want to suck water out the river and pump it to these houses, A and B. All right, and so we're saying, where should we put it along this stretch, this 5 kilometre strip? Where should we put the pump so that here we're putting pipe here, we're putting pipe here. Where should we put the pump so that we use the least amount of pipe? All right, so we're going to solve the problem like this, real life world problem application of calculus. We're going to solve this using calculus methods. So let's define this length. This is where we're going to make our own argument here. Let's let xn equal x. Okay, from here to here, this is x, which means xm is going to be 5 take away x. All right? So if this distance is x and this distance is 5, this distance is 5 take x. All right? Now the length we're interested in, the total length of pipe, is going to be ax plus bx. So that's what we're trying to come up with an expression for. So ax, just using Pythag, is going to be, so we're going to have, let's make it like we would with Pythag, 2 squared plus 5 take x squared equals ax squared. And so therefore ax is the square root of 4 plus 5 take x squared. That's our expression for ax. We need an expression for bx. So same again, 1 squared plus x squared. Okay, so we defined x, we defined 5 take x. So therefore, the total pipe, so we've got pipe going from here and pipe from here, is going to be ax plus bx, which is going to be square root of 4 plus 5 take x squared, plus square root of 1 plus x squared. All right, so we've built up that equation, okay, so this one's a little bit harder, so maybe 3 marks there. And then, okay, again, we're performing that same optimization process. Differentiate, find the optimal solution, answer the question. Cool, I think that's enough. I've had enough. So you guys have to.